Okay, any questions before we begin? Yes?
Why in DC circuit kinetic energy do not change?
Which kinetic energy?
Charge from minus terminal and plus terminal flow, like kinetic energy does not change or change?
Well, I think this is the problem. Let's just assume we have a metal, some kind of a resistor. Okay, we had discussed that the electrons in this is a part of a wire. The electrons will be doing some random motion. In the absence of any electric field, the electrons will just move randomly around. And on the average, they will just stay where they are. So this electron will always stay there if there is no electric field. Now, if there is an electric field, let's say in this direction, and of course the electric field exerts a force on the electron. So the electron will accelerate, and hence its kinetic energy will change. I mean, depends on in which direction it was initially moving. But what happens is, let's say, it starts from here. Let's say at a given instant it is moving in this direction. It is accelerating in this direction. Then when there is an electric field, it will gain, its kinetic energy will increase because the electric field will be doing some positive work. Its kinetic energy will increase, but then it will collide with an atom over here. So there is an atom over here, then it will collide with it and just change its direction. Now, during this process, some of its energy is transferred to the atom. Now, if its kinetic energy increases a lot, then it's more likely that it will transfer more kinetic energy to the atom. So on the average, we assume that the kinetic energy it gains due to this electric field, it does gain kinetic energy, but during these collisions, it loses, on the average, all of that kinetic energy. So that is why we assume that Vd is constant. Although there is an acceleration, we still assume that the drift velocity is constant, and observation also confirms this assumption, mainly because as the electrons are colliding with the atoms in the wire, they will be losing the energy that they have gained. Yes, other questions? Many batteries. Okay.
Do we know exactly how the charge goes there?
Now, let's do an example. I mean, it's important that you understand how we determine the signs. So let's do an example. Let's assume that we have such a system. Before solving the equations, I don't really know which direction the current is actually flowing. Well, in this one, it turned out to be simple. Let's just change it. Now, what will happen is this battery will try to run a current in this direction. This battery will try to run a current in this direction. Now, the complications will arise. Let's say this battery runs a current in this direction. If this battery was not there, we know that as the current is running through the circuits, it will split over here. Some of it will go through this resistor in this direction, and some of it will go through this resistor in this direction from right to left. But this battery over here will try to run the current in the opposite direction. So it will depend on how powerful each one of these batteries are, what is the relation between these resistors which will determine the current that is running in this wire and in this wire. The current in this wire will definitely be running in this direction because both this one will try to run a current in this direction, and also this one will try to run a current in the same direction. So the current here will be running in this direction. I can say that. But I cannot really say what will be the current in these wires, what will be the direction of the current in these wires. So I cannot really determine it. But I don't need to make any assumption on the directions. So let's write the equations that will allow me to determine the directions of these currents. Let's just give some names. Let's say the resistors are R1. Now this is R3, R1, R2. Epsilon 1, this is the EMF of this battery, and epsilon 2 is the EMF of this battery. Now the first thing I have to do in such a case, let's also add a capacitor somewhere. Now the first thing we have to fix is what will we mean by a positive current and what will we mean by a negative current? What is the positive and negative direction of the current? So I will call the current running on this wire to be positive if it is running in this direction. So let me just put a sign there, and let me name it I1. I don't really know whether I1 is running in this direction or in the opposite direction. The only thing I'm saying is that I will say that I1 is a positive current if it is running in this direction. If at the end of my calculations I find that I1 is negative, then I will know that this current is running in the opposite direction. Let's look at this wire. Again, I will call the current in this wire to be positive if it is running, let's say, in this direction. Why do I choose that direction? Well, up to you. I mean, I can choose whichever direction I like. So I can just choose this one to be my positive direction. So this I1 will be running over here on this wire also. This is I1. And now for the current in this wire, I will also call it to be a positive current if it is running in this direction. Well, if I look at this point, the total current entering this point is I1 plus I2 plus I3, and there is no current running out of it. So that already gives me one equation. For my unknowns, I1 plus I2 plus I3, this should be equal to 0. So this equation already tells me that at least one of the currents have to be negative, which basically tells me that at least one of them should be running in the opposite direction to these arrows. At least one. Which one, I don't know. I mean, it will probably also depend on the resistances of the resistor and the EMFs of the batteries. But I don't need to know before writing this equation. Now the next thing, okay, I fixed the signs of the currents. I fixed what I mean by a positive current or a negative current. Now I have to do a similar thing for the capacitor. I will say that the capacitor can be both positively charged or negatively charged. Remember, when we were discussing the capacitance, we defined the charge of the capacitor to be a positive number. It was the charge of the positive plate. That was how we defined the charge on a capacitor. Now we have to pay attention to the signs. What do we mean by a capacitor that is positively charged, and what do we mean by a capacitor that is negatively charged? Now I will say that the charge of this capacitor is the charge on this plate that is connected to this wire, which can be positive or negative. If it is negative, it just tells me that this plate is positively charged, this plate is negatively charged. So let me just put plus over here, the minus over here, the charge is Q. Now, if I don't know whether this plate is positively charged or not, I don't need to know it yet. The only thing I know is that if at the end of my analysis I find that the charge of the capacitor at a given instant is, let's say, 5 coulombs, I will know that this plate is charged 5 coulombs, this plate is charged by minus 5 coulombs. If at the end of my analysis I find that the capacitor is charged by, let's say, minus 2 coulombs, then I will know that this plate is charged by minus 2 coulombs and this plate is charged by plus 2 coulombs. Again, that will be, my analysis should tell me. I'm not making any assumptions here. Now let's relate this Q to I1. Now I1 is nothing but the current running through this point per unit instant, per unit time. But this current will decrease Q. Let's say if at this point in, let's say, if I have a current I1 equal to 1 ampere, then I know that from this point, per second, there is a 1 coulomb of charge passing through this point. But let's say I started with a capacitor that has a charge of 2 coulombs. So this was minus 2 coulombs, this plate over here now arrived at, after 1 second, 1 more coulomb. So the charge in this plate becomes just 1 coulomb. So if I1 is positive, with time, Q will be decreasing. Do you agree?
If we would choose inverse plus of the current capacitor will be below, it would increase.
True. If we had chosen this plate, the charge to be the charge of this plate, then if there is 1 coulomb coming in and my capacitor has a charge 2 coulombs, then that would have mean that this plate is charged by 2 coulombs, another coulomb arrives, so it becomes 3 coulombs, so the charge increases. But with this choice of the signs, if there is 1 coulomb that runs through this wire, the charge in the capacitor decreases by 1 coulomb. So I can say that I1 is equal to, well, this is the definition, dq by dt. Q is the charge that passes through this point. This is the definition of I1. But if dq passes through this point, then Q decreases by the same amount, minus dq by dt.
Why is it decreasing?
This one. Well, let's do an example. Let's say that dt is equal to 1 second. Q is equal to, give me a number. 2. 2 coulombs. And dq is equal to 3. Now, 0.3, let's make it. So the current I1 in this example is 0.3 coulombs per 1 second, or 0.3 ampere. So this is the current running through this wire. Now, initially, this plate, the upper plate, was charged 2 coulombs, and the lower plate was charged minus 2 coulombs. Now there is an additional charge of minus 3 coulombs that reaches this plate. So minus 2 coulombs, that was the initial charge. Now there is a 0.3 coulombs that arrived after 1 second. So the charge is minus 1.7 coulombs. And since the current in this wire and in this wire, they are the same, if 0.3 coulomb arrives at this point, 0.3 coulomb also passes through this point. So the charge in the upper plate now became 2 coulomb, that was the initial charge, 0.3 coulombs left, so we are left with 1.7 coulomb. So what we have is the change in the charge of my capacitor is minus 0.3 coulomb. Remember, Q is the charge of this upper plate. dq is the change in the charge of this upper plate. The final charge is 1.7 coulomb. The initial charge was 2 coulomb. So the change in the charge of the upper plate is minus 0.3 coulombs, which is nothing but minus d small q. So this is why here we have this minus sign over here. The small q, which is the current passing through a given area per unit time, is equal to minus dq, the change in the negative of the change in the charge of this plate. Any questions on this one?
Hocam 6-2 C olan plate'ten neden çıkardığınızı anlayamıyoruz.
From here, you see, the current tells me that if I take this point over here, after 1 second, 0.3 coulomb moves from the left of that point to the right of that point. I can do the same thing at this point, which tells me that 0.3 coulombs moved in this direction.
Ama önce gidip sonra gidiyor.
And I can do the same thing over here. At this point, 0.3 coulomb moves from this point to that point. So there's 0.3 coulombs arriving on this plate and 0.3 coulomb leaving this plate. So these plates are not connected. These charges cannot move to the other plate. This 0.3 coulomb is on this plate now. Initially, we had minus 2 coulombs there. Now there is additional 0.3 coulombs arriving due to the current. So this is the new charge. In the above plate, there was 2 coulombs, but due to this current, 0.3 coulomb has left my plate. That is why I subtract.
Aralarında bir bağlantı olsa.
Sure. The current is not transferred from the lower plate to the upper plate. The charges are not transferred from the lower to the upper plate.
If you calculate the opposite direction,
If
current flow opposite direction,
let's do it, that example also. If current flowed in the opposite direction, again, let's take dt is equal to 1 second, q is equal to 2 coulomb, but this time dq will be equal to minus 0.3, no, dq is equal to minus 0.3 coulomb, minus just telling that it's moving in the opposite direction, and so that I1 will be equal to minus 0.3 amperes. So let's see, here is the battery, which is connected to the wire that has this current I1. Well, due to this minus sign, the current is actually running in the opposite direction. So initially we had plus 2 coulombs on the upper plate, minus 2 coulombs in the lower plate. So if we wait 1 second, a charge of 0.3 coulomb will move from this negative plate to here. This is 0.3 coulomb. Here I don't put the minus sign because that minus sign is just telling me that the charge is moving from the plate to this point. It is crossing this point in this direction. And there will be a similar thing on the top point. So there will be a 0.3 coulomb in this direction. So when we see the charge in the upper plate is now 2 coulomb plus 0.3 coulomb, which is 2.3 coulomb. The charge on the lower plate is minus 2 coulomb minus 0.3 coulomb. So this is minus 2.3 coulomb. Well, these two have to be equal in magnitude, opposite in sign, because the capacitor is, as a whole, is neutral. It's just the different plates have different charges. And so the change in the charge in this on the capacitor is the final charge is minus 2.3 coulomb. No, the final, yeah. No, the final is plus 2.3 coulomb. The first charge is 2 coulombs. So this is 0.3 coulomb. So dq is 0.3 coulomb, which is minus d small q, because the small q was minus 0.3 coulomb. So whichever direction the current is running, whether it is running in this direction or in the opposite direction, there is always this minus sign, and hence there is always this minus sign between I1 and the rate of change of the charge of the capacitor. This relation is independent of which direction the current is running. It's always minus. So if the current is running in this direction, positive charges will be arriving in the negative plate, and hence the charge in the capacitor is decreasing. So dq by dt is negative if I1 is positive. So hence we have to have this minus sign. If I1 is negative, that would mean that the current is running in this direction. Positive charges are leaving the negative plate, leaving it even more negative. That would mean if the charge in the capacitor is increasing, if I1 is negative, which means dq by dt is negative dq by dt is positive if I1 is negative. Again, the same thing. So in both cases, no matter what the direction of I1 is, the I1 is always equal to minus the capital Q by dt, where this capital Q is the charge in the capacitor. Now, how many unknowns we have? 3 or 4? So let's see, what are the unknowns? So you claim that you know Q? No, that makes 4. So we have 4 unknowns. We need to write 4 equations for these 4 unknowns. Now we have one equation is over here relating 2 of our unknowns. Another equation is over here relating 3 of our unknowns. We still need 2 more equations for our unknowns. And to determine those 2 more equations, we can use the Kirchhoff's rules. So let's see. We have to choose some loops. We have to start from a point and go around the circuit whichever way you like, but you should go around the circuit and come back to the same point. It's again, you can choose this loop, you can choose this loop, or you can choose this one, or you can choose start from here, go around this a couple of times, go around this a couple of times, and come back over here. All are valid. You can use whichever one you want. It's all up to you. Just choose 2 of them. Let's choose 2 small ones. One will be this one. Let's say this is L1, the loop 1. The other one that I will choose will be this one. This will be my loop 2. So what do you want? Okay, as you wish. So you want to go the other way around. Okay. And you want to go around what point? Well, it's already in R3. I mean, it goes in R3. I could have as well went over this one. But let's just do this one. I mean, it's completely up to you. Just choose 2 loops that you like. Now let's start with loop 1. Again, you can start from whichever point you want around this loop 1. This is loop 1. Let's start from this point. We start from that point. Now, from this point to this point, what is the potential drop?
0.
From this point to this point, what is the potential drop? I3 times. From this point to this point?
0.
Let me write this I3 R3. I3 R3 plus. From this point to this point, what is the potential drop? Minus I2 R2, because we are going in the opposite direction of the positive direction of the current. And from this point to this point, what is the potential drop? Epsilon 2. This is equal to 0. So this is our third equation relating our 4 unknowns. Now let's come to the loop 2, this red one. We are going in the counterclockwise sense. Let's start from this point. Okay, from this point to this point, what is the potential drop? I1 R1. From this point to this point, what is the potential drop? Let's say the capacitance is C. Minus Q over C. Well, the potential difference across the plates is just Q over C. It's minus because we are going from the minus plate to the plus plate. If Q is positive, there is a potential increase over here, not a potential drop. That's why we have minus over here. Now, from this point to this point, from this point to this point, over this R3, minus I3 R3. And then from this point to this point, 0. From this point to this point, minus epsilon 1. And we are done. We are back to our initial point. So we have 4 equations to be determined for the 4 unknowns we have. Now physics is over. The rest is we have to do the algebra. I mean, you will have to do the algebra. You cannot run away from it, but after this point, there's not much physics left.
If you current I3 in the opposite counterclockwise, is that problem?
So you are saying that why don't we choose I3 in the opposite direction? No? Let's see what will change, what will be our equations. Now we have chosen I3 to be in the opposite direction. Now we didn't do anything with I1. So I1 will be equal to minus dq by dt. Nothing changes over here. This doesn't involve I3. Now I3 is involved in this charge conservation at this point. So what is the sum of the currents entering this point? The sum is I1 plus I2. These are the currents entering, and those leaving? I3. This is our new equation. Or we can write this as I1 plus I2 plus minus I3. This should be equal to 0. Well, that minus I3 is, well, we just changed the positive sense of the current. So if initially we had the solution gave us 1 coulomb, now it should give us minus 1 coulomb. So this is why we have this minus sign over here. This equation and the previous equation are identical. Just this difference is only due to our conventions. Now let's just look at one of them, L1. What changes in L1, in the loop? Shall we go the opposite way? Counterclockwise? Rather than clockwise. Just to have a change. Now, from this point to this point, what is the potential drop? Minus epsilon 2. From this point to this point, what is the potential drop? I2 R2 is plus because we are in the same direction as the positive direction of the current. Now from this point to this point, from this point to this point, I3 R3 plus. And this should be equal to 0. Well, I can also write the same equation as epsilon 2 minus I2 R2 plus minus I3 R3. This should be equal to 0. Now let's just compare it with what we had before. This is what we had before. This is the new equation we have. Epsilon 2, identical, minus I2 R2 identical. The only change is here we have plus I3R3. Now here we have minus I3R3. That's the only difference because we changed the positive sense of I3. And basically it will be the same. We will have, if you write the loop expression for this L2, we will obtain exactly this expression with the only modification that I3 will be replaced by minus I3. So whichever direction you choose your loops, whichever directions you choose for the positive direction of the currents, you will always get the same equation with the understanding that you have changed the convention. So you can choose whichever direction you want, whichever loop you want, all of them will be correct. R2 and R3? No, we cannot. There's a battery over there. They are not connected in series, neither in parallel. We cannot replace them with an equivalent resistance. Well, of course, you can ask the question, what should we do? What should we replace all of this thing? What should be the resistance that we should use to replace all of this thing so that we can have the same current? Then you can define such an equivalent resistance, but that equivalent resistance will also depend on epsilon 2, not just R1 and R2 and R3. You just calculate the current running through epsilon 1 divided by the, let's say, epsilon 1 divided by the current. That gives you a resistance. You can define such an equivalent resistance, but it's not really of much use.
Still not convinced why a current takes for a given circuit the zero resistance path.
The wire. So your question is this one. Let's take a simple circuit. Like this one. We know that I will be equal to epsilon over R2. Because I will just come over here. This will be also I, this will be I. So it will be as if this R1 is not there. Right? Now the question is, what is a zero resistance wire? A short, I mean, okay, it's a short, that's what the name is, but what causes it to have zero resistance? What's the property that makes it to have zero resistance? You see, zero resistance, okay, a superconductor will be zero resistance, but you cannot connect it to a battery. Zero resistance, which will also mean that there is no potential difference between these 2 points. There is no electric field between these 2 points. Whereas there is some electric, I mean, if this had a very small resistance, then we would have some potential difference between these 2 points. But there's no electric field in this wire. There's no current running through this one. Again, there is no electric field in that wire. And what the zero resistance wire does is, you see, the electric field in a metal builds up because one side of it will have some extra charges and the other one will lack some charge. So one side will be positively charged, the other side will be negatively charged. That is why you have some resistance. And the charges, some electric field and a potential difference. Now the resistors, conductors, will basically let these charges move from one side to the other one. So if you have a resistor, let's forget this one. Okay, here we have a resistor. There will be some charges accumulated at this end. There will be other charges accumulating at this end. So there will be some electric field over here. Okay, so because this resistor only takes the charges from this, although it's a conductor, it takes some time for the charges to move from this point to this point. So that's why there will be some buildup. When you turn on the circuit initially, there will be some buildup of charges. But in a zero resistance wire, whichever charge reaches this point, it is instantly moved to the other point. So there is, let's say, the charges reach over here. This resistor tells them, oh, hold on. You will take some time to move over there to the other side. But then there is this wire which just tells them, takes them to the other side instantly. So you cannot build up any charges between the ends of this resistor. So since you cannot build up any charges, there won't be an electric field created in this resistor. So there won't be any current created in this resistor. Because whichever charge reaches this point, this wire already takes it to the other side.
Even if it wasn't steady current?
If it is not a steady current, well, if it is not a steady current, things will be different. This is for a steady current. Steady at least in the sense that we don't have alternating current. This won't be a steady current no, this will be a steady current. And when we have alternating currents, things will get a bit more complicated, but for the timing, let's just keep with simple resistors, simple batteries, simple capacitors. You see, sorry to interrupt. Just think of it like this. So let's say that a group of people are rushing from top to bottom. Okay, so you are a resistor over there. So they come and some of them will go through you, some of them will just run through this corridor. So they reach that point, and you say, no, just wait a bit. Well, why should they wait? They just cross. It's the same thing over here. Well, if he also stops them at this point, I mean, he tells them, okay, I will let only 5% to pass per second, and you tell them that you will let 10 people pass per second. Okay, some of them will pass through him, some of them will pass through you. But if he just lets them pass straight away, all of it will pass through the corridor.
If the electric field in the I wire is zero, what is pushing the electrons to the charge?
You see, the battery is already pushing them from one side to the other side. So this battery is already pushing them. But these resistanceless wires, they just allow them to move until the first resistor. So this is already pushing them. This pushed it. So all of them moved one. They all reached over here.
They can be driven by the external electric.
In a sense. Yes, your question now.
Can you just plot a electric potential graph for a circuit? Like how the time changes from one end of the battery and to the other end of the battery?
Well, let's see. Let's look at this one. Will this be enough for you or too simple? Epsilon R1, the point A, the point B, the point C, the point D, let's say this is the point B prime, this is the point C prime. And now there's one problem. Should we set one of the potentials to be zero at any given point? And we can set the potential whichever value we want. We can set it to zero at a given point. Now, we cannot set the potential both at B and C to be zero. There is a potential difference between B and C. But one of them we can set to zero. Let's say we set B to zero. This is what we call grounding. This is the ground. So we just set the potential at B to be zero. So this is the potential as a function of the position on this wire. So let's say this is the point A, this is the point B, this is the point B prime, this is the point C prime, This is the point C. This is the point D. What is the potential at A? 0, because there is no potential difference between A and B. There is no resistance. This is 0. From A to B, it's 0. From B to C, it's again 0. Now, from what is the potential of C prime? Let's say there's a current running through the wire, and I will be epsilon over R1. So what is the potential difference between, well, is B prime or C prime at a higher potential? B prime is at a higher potential because the current is running from B prime to C prime. So when we reach C prime, the potential at B prime, there was a 0 potential. At C prime, there will be a negative potential. Well, how it changes, well, we don't really know. It depends on the properties of the resistor or whatever we want, whatever you use. But let's say it changes like this. Now, from C prime to C, the potential difference is 0. From C to D, again 0. So this is the potential graph.
Well, yeah, right now I can ask my main question. Is that these wires, we think that they are without resistance. So I was thinking that these charge carriers, positive charges, must be moving from higher potential to lower potential because there's no energy. So if these wires have a flat, so why would they even move?
Well, you see, the problem is the idealization we are making. The wire, I mean, if this is there's no resistanceless wires. All the wires have resistances. So actually, for an actual realistic circuit, what it will look like will be this one. They are not flat.
The ideal case is not true.
Of course not. Now, what we do is we just say that, okay, the whole resistance of this wire, we are just showing it over here. So because they are connected in series, so in series we can just replace it with an equivalent resistance, and this R1 is nothing but the equivalent resistance of the resistor we put plus the resistance of these wires.
Let's say in the B point, I think there's two-way for the current.
There's?
No, B point. Yeah, two-way to the current for current. And,
Why?
To the ground or to the...
You see, not really, because the battery takes charges from the negative, takes positive charges from the negative terminal and gives positive charges from the positive terminal. So if you want to say it like this, there is an I current moving in this direction, some I prime current moving to the ground, plus I prime current moving from the ground. So there won't be any net current over here. Now, you don't also think of it in the form that, okay, the current just started from here, it reached this point, so it has to decide. No, it doesn't decide. So already when you connect the circuit, the electric field forms everywhere, and the electric field determines which direction the current will flow at every point. So there is no current starting from here, reaching this point, and then deciding where to go.
So I would understand your answer why there's no current in ground.
There is no?
Why there's no current in ground? Your answer.
So let's see. Let's say that this is I prime, this is I. So what will be the current over here? Current over here on this wire? I, okay. Well, if you are agree that it is I, then I prime has to be 0 because let's write the loop rule, the current rule at that junction. What is the sum of the currents entering that junction? I. What is the sum of the currents leaving that junction? I plus I prime. I prime has to be 0.
Mathematically it has to be, but what about the physics behind it?
Why should the current move there?
Well, why shouldn't it move there?
Why should it? I mean, you see, if there, in physics, if there is not no force acting on you, you will not move anywhere. You will not change your motion, let's say. So the influence of this battery is just to give away I current and take away I current from here. So I will be taking the current from this side and giving away current on this side. So the current that I take should be equal to the current that I give. So this is why the current over here is I, the current over here is I. So where will this I come from? Of course, you can say that this I, if you want to say that this I, when it reaches here, it somehow, for some reason, splits. Then there won't be an I coming over here, but that means is you are charging the battery acquires a net charge, and the batteries don't do that. So what the battery does is it has to also take this charge, this current I. So if only a part of it comes from this junction, from this current, it should take the remaining part from the ground. So if there's I prime leaving here because of this current, there should be an I prime coming to this junction because of this current. The net current on this grounding wire will be 0.
So can we say that the ground has almost infinite resistance? Because if we say that infinite resistance, in the same case, the current going through there would be 0.
Not really. What we say is ground has zero potential. So we say this point has 0 potential. So whatever we connect to this one, this point also has 0 potential. There is no potential difference. So there cannot be any current running through it. You see, the battery creates a potential difference, but it doesn't really fix the potential at any point. So by connecting it to the ground, or whatever you call the ground, you are fixing the potential at a given point to be 0. That's the only thing you do. The potential differences do not change.
Coming back to the graph that you said that we accumulate all the resistors that the wire and the resistor has and writing it as R1. So shouldn't we...
You see, a battery is also not just a long rod and a small rod. This is just schematic view of the circuit.
What I was asking for the graph, the potential difference must be equal in the ideal case and the real case. So the graph should be wrong, is it?
True. Because the current will be smaller now. Because now the total resistance of the wire is this resistance of this resistor plus the resistance of the wire. Or another way, if R1 is the total resistance, then the resistance of between B prime and C prime is actually smaller than this R1. So the potential drop between B prime and C prime will be smaller. Happy now? Okay, let's give a 10-minute break and we will continue.